have both generation and recombination. And for the generation, it's related to this, for the recombination rate, it's related to the electron concentration and Hall concentration. And this alpha is just a constant. And in equilibrium, the generation rate should be the same as the recombination rate. So this NR, this NP is basically Ni squared. And the generation, we use symbol G sub I, so this is due to the thermal generation. And in addition, if we shine light on the semiconductor material, we will have additional generation mechanism. And this is basically just called optical generation. Basically, the electron can absorb a photon and then it jump from the valence band to conduction band. Okay. And for this generation rate, just pay attention to the unit, right? So this is centimeter cube per second. So this basically it's number of electron hole pair created per centimeter cube per second. Okay. And then if we continuously shine light on a semiconductor material, we will have these excess carriers. So the excess carrier is related to the generation rate, and this is recombination lifetime. Okay. So if we want to calculate the total electron or concentration, so it's basically the equilibrium value, and not plus this delta F. This is excess value. Right. We also discussed what can happen if we turn off the light. So if we turn off the light, so these excess carriers will decrease. Right? And basically, this the change of these excess carriers can be described by this equation. Okay. So basically, this excess carrier decays exponentially. So eventually, it will go to 0. And we also introduced this photoconductivity. So this is because this light can create excess carriers, and these excess carriers can increase the conductivity. So then we can calculate the conductivity increase delta sigma. So it's related, basically it's due to the enhanced carrier concentration, delta N. And we also can calculate this photoconductivity. Basically this conductivity increase times the electric field. Okay, so here are these new topics we will discuss today. So we have introduced this general continuity equation. Right? So we already derived this, and then we will try to derive a limiting form for this minority carriers. Right? So this is general equation. And if we consider minority carriers, we can simplify this continuity equation. Okay. And this simplified version is called minority carrier diffusion equations. Okay. And then we can use these minority carrier diffusion equations to solve 4 different physical conditions. Okay. And then I'll also show you some examples. Right. So here, this is general continuity equations we discussed in the last lecture. So we are interested in how does this carrier concentration change with time in this shaded box, right? So basically, several things can change the carrier concentration inside this box. So we can have this current flow line. So current flows in can increase the Hall concentration, and flows out can reduce Hall concentration. And this net change is basically due to this flows in minus flows out, right? And also it's related to the recombination. So here this recombination is always happening. So the recombination can reduce the carrier concentration. So that's why we're on minus side. And recombination is driven by this delta P over tau sub P. And besides these two, we also have this optical generation, right? So if we have light shining on the material, we have this continuous optical generation rate, so G op, right? And based on this equation, we can divide by delta x on both sides, and we can get this continuous equation for hole. Okay? And we can do the same thing for electrons, right? So the only difference is we have a minus sign for hole, but for electron, there's no minus sign here. Okay? Right? And in general, right, these things can vary by in 3 dimensions. Okay, so here we have this, considered x direction. But if we consider all the 3 directions, we can change this term by this, this gradient function, right? Gradient function, right? And this is the general, continuity equations for electron, and this for holes. And again, you can multiply by Q. If we multiply Q, or negative Q on both sides, so this for electrons and this for holes, right? And then if we add these two together, okay, so multiply this minus Q or plus Q on these both sides for these 2 equations, then we can have, let's see what we can do. So we can okay, so if basically we can add these two together, add these 2 equations together, right? So this left 2 terms, if we add them together, basically this will be partial rho over partial. Rho is the total charge density, right? Basically, this rho is equals minus Q times P plus Q times P. Okay, so minus Q times N plus the Q times P. So this is the total charge density. And then if we look at these, these terms on the right, because we have minus and this plus, right? So these terms cancel out. Right? So if we add equation 1, so these 2 terms cancel out because we have minus and plus, right? And also this term cancel because this delta n is basically delta p. That's same. Okay, and then this J here, this J here will be, because we have this minus sign, right? And also this minus sign here. So if we add them together, we have Jn plus Jp. So that's J total. So basically, if we have this equation 1 and equation 2, if we have this equation 1 plus equation 2, we will get this. Okay? And this will be the charge continuity equations. And you may have learned this equation from EE133. Okay. Right? So here in our lecture, our course we will mainly use these 2 continuity equations for each charge carriers. Okay. Right. So now let's try to derive a limiting form of this general continuity equations, and we are focused on minority carrier. Okay, and which is known as this minority carrier diffusion equation, or MCDES. Okay, so we'll try to define the notation and terms, and we will also make some assumptions. Okay. And then we can determine 4 different general solutions for this minority carrier diffusion equations, corresponding to 4 different physical conditions. Right. So first, let's define some new notations. So we have this. For the minority carriers. So what what are minority carriers? Anyone still remember? I think we discussed that like this week or either last week. So what are minority carriers? Yes.
Is it like an electron in a mostly whole section?
Yeah, exactly. So it's electron in the p-type region or holes in the n-type region. So these are the minority carriers. So here we can define these notations like this. N sub p basically means this is the electron in the p-type region, or p sub n. So it's the whole concentration in the n-type region. Okay. Right. So these are the minority carriers. Then how can we define majority carrier? So what are the notations you can use for the majority carrier? So here this n sub p or p sub n represents minority carrier concentration. Right? So for majority carrier, what are majority carriers? Majority carriers basically electrons in the n-type region, right, or holes in the p-type region, right. So then these carrier concentration can be presented as n sub n or p sub p, right. So these are the majority carrier concentrations. These are here, right? Okay. And sometimes we also add this, the subscript 0 here. So this basically means the equilibrium condition, right? This here 0 means equilibrium condition, right? And it can combine with this subscript above, so we can have this n sub p0 or n sub n0. So these are basically mean. So this would be equilibrium whole electron concentration in the p-type region, right? Or this will be the equilibrium minority electron concentration, right? So this would be the equilibrium majority electron concentration, right? And total concentration can be written as this equilibrium component plus a non-equilibrium component. So this is also we have showed you before. So this is the total concentration, and this is the equilibrium part, and this is the non-equilibrium part, or the excess term. Okay, so now, so these are the notations. Now let's look at the assumption. Right? So we are trying to make several assumptions to simplify this continuity equation. So first assumption is that the diffusion current is the drift current is much smaller than the diffusion current. Okay, and for these minority carriers, it means that the current is basically the diffusion current. Right? So we have this is a total current. So which part is the diffusion contribution? 1 or 2? 2, right? For the diffusion current, do you still remember what the drivers was? Yeah, exactly. So this is the gradient, right? The gradient in carrier concentration. So this is the diffusion current. And here the drift current, the driving force, the electric field. So this first, the part 1, term 1, this here is the diffusion current. So now we can ignore this drift current, right? So this part is 0. So the current is basically dominated by the diffusion current, right? Okay, so this would be the equation we are used to determine the current. So this is the hole diffusion current, and this is electron diffusion current, right? Now, the second assumption is that the minority carrier concentrations are equal to the excess carrier concentration. Okay, so it means that basically we have this this excess term or this non-equilibrium term. This delta P sub n is much larger than this P sub n0. So this is the equilibrium, right? So this is the equilibrium term, and this is excess term. So and it's same for for electron. The delta n sub p is much larger than p n sub p0. Okay. So for this, this assumption, we will see that this minority carrier concentration, right? This minority carrier concentration is dominated by the excess term. So basically, we just need to use this equation, right? So if this delta term, this non-equilibrium term is much larger than the equilibrium term, so we can basically ignore this equilibrium. So this NP is equal to delta n sub p, right? And same for poles. Right? For poles, it's P sub n is same as delta P sub n. Okay, so it means that the non-equilibrium component is several orders of magnitude larger than the equilibrium component, right? So based on this assumption, we can rewrite this derivative term here. So we have this d np over dx. So this is carrier gradient, right? So this is gradient in carrier concentration, which will be derived with minority carrier equation. These two equations are very useful when we introduce p-n junction. In p-n junctions, we also want to understand how does this carrier changes at the interface between this n-type and p-type materials, and also use these minority carrier diffusion equations. We can determine the current in the p-n junction. Okay, so we are using these two equations later, but today I will show you several four simple physical conditions for this like either a single material or p-n junction, right? Okay, so today we'll try to discuss these four special cases. Okay, so we have this steady state no light, plus this no recombination, or steady state no concentration gradient. And last one will be no concentration gradient plus no light. So for these four special cases, we will write the solutions for this delta Pn, and this delta Np will have the exact same form. This excess terms are the same. Okay. So any questions so far? Okay, good. Now let's look at the first case. So first one is steady state no light. And let's just use this continuity equation. Sorry, this is minority carrier diffusion equations here. Okay, so for this case, can we further simplify this equation? So for no light, what does it mean? Yes, GOP, right? So basically this OP is 0, right? So this optical generation rate is 0 because no light. And how about the steady state? Yes, exactly. So it's not changing with time or any time derivative is 0, right? So then we will see that so this GOP is 0, right? And then this part, right? The first part is because steady state, time derivative will be 0. And then we can simplify this minor carrier diffusion equation. Okay, so then we can write as basically, this general equation will be like this. So this is the E related to diffusion, right? And this is related to the recombination. And for this equation, you can see this is basically this P is we want to solve, right? We want to solve this delta P sub n, right? And this is the second order differential equation, and we can solve this easily. And this is the general solution. Okay, so it's any constant a times exponential negative x over exponential x over L sub p, and plus b. B is also constant times exponential x over L sub p. Okay, so this a and b are constants, and for particular for certain questions, for certain cases, we would like to solve this a and b based on the boundary conditions. Okay, so for them we can get some values for when x equal to 0, right? So maybe there's some initial values, and also when x is infinite, there may be also certain values. Okay. So based on these boundary conditions, we can solve for a and b. So this this expression is the minority carrier diffusion equation, the solution 1. Okay, right? And in this equation, we also have this L sub p, and L sub p is called minority carrier diffusion length, and this diffusion length is related to the recombination lifetime and diffusion coefficient. We have the equation here, right? So this diffusion length is basically square root d times tau. Okay, so this d here, again, d is the diffusion coefficient, and diffusion coefficient is here. Right? And what's the relationship between d and mu? You must still remember, we just introduced the Einstein relation, right? So d over mu equals kt over q, right? So this is the relationship between diffusion coefficient and the mobility, right? So here this L sub p is the diffusion length. So this is the average distance that a minority carrier diffuse before recombine. Okay. And I will show you some values for this diffusion length. Usually it's like micrometer scale. Okay. Right? Okay. So let's just use this solution 1. Let's look at a particular example. Right? So if we have something, or like whatever it's applied bias in a p-n junction, is keeping this delta p sub n at x equal to 0 fixed at certain value, which is this delta p sub n. And then in the n region of the p-n junction, let's write down the the exactly solution. So we have the general solution. Right? We have general solution, and then we need to apply the boundary condition to solve for A and B. Right? So when we apply the boundary condition, we will see that eventually we will get this solution here. So I'll show you this later how to solve. Okay. So basically you will see something like this. Okay. So this delta p sub n is this delta p sub n times exponential minus x over LP. Okay. So it tells us that this excess carriers decreases exponentially, right? And this would be similar as we discussed before, right? So if we plot this excess carrier, right? This delta p sub n as function x. So we have some initial values, and eventually it will go to to 0. And this initial value here is given by this delta p sub n, right? Okay. Right. So this is a steady state, like no light. And so basically this excess minority carriers concentration decays away exponentially as you move away from the junction. Okay? And this decay length is this L sub p. Right? Okay. So that's the first solution. Let's look at the second case. So for the second one, we will have this steady state, no recombination, and no light. And I think this is even simpler, like simpler than the first case, right? So for this one, for steady state, what does it mean? This term will be 0, right? This time derivative, this term is 0. No recombination. Or let's put it in no light. For no light, this COP is 0, right? And how about no recombination? Which term will be 0 or this term, right? This term will be 0 because this term represents this recombination. Okay, so this delta p sub m over tau represents recombination. So then we have this first term is 0, the third term is 0, and the last term is 0. So this basically we have this term equal to 0. Right? Okay, so this will be the simplified equation for case number 2. Right? And this can be solved easily, right? So this is also a differential equation. And the general solution will be like this. Okay, so it's basically a constant A plus constant B times X. Okay, and this term tells you that this kind of this carrier concentration varies linearly. So here is different, this exponential decay, and for this case 2, we have kind of linear decay. Okay. Right, so this is the general solution, and again, for A and B, for certain case, we need to solve this A and B, right? And we can get this the actual value for A and B based on the boundary condition. Okay, so right, so this is solution number 2. Any questions? Okay, right, good. So now let's move on to the third case. So for third case, steady state, no concentration gradient. steady state, this turns 0, right? And how about no concentration gradient? What does this tell us? Yes,
The diffusion term here,
diffusion term. We have which term?
the
Yeah, this one, right? So this is time. This is the gradient, right? So this is the kind of gradient in air concentration. So this term is 0, right? So we'll have this 0 and this 0, and then we can write the simplified equation. Okay. So now what's the solution for delta P sub n? What's the solution for delta P sub n? Yes.
GOP times the
Yes, GOP times lifetime. So this looks familiar to you, right? So this GOP times tau, and this is general solution. So now if we go back to the, in the beginning, here, right? So we have discussed the excess carriers, right? If we have this continuous light, and the same here, right? So if we have this continuous light, this excess carrier is basically object generation rate times recombination rate times tau. Okay? Right? So this shows that both electrons and hole densities increase by this G times tau. Okay, so this is the solution for the third case. Right, so this last one will be is no concentration gradient and no light. Okay, so again for no concentration gradient, the second term is 0, right? Okay, right. So here is just a quick summary for these 4 solutions. So to these 4 different cases. Okay, so we have this is no steady state, no light, steady state, no light, plus no recombination, steady state, no concentration gradient, plus light. So we have light, we have light. Or no concentration gradient and no light. So these are the 4 solutions. Yes.
Is it the same formula for NP?
Yes, yes. It's delta n sub p have the same expression. Yeah. Okay, right. So now let's use these mitotic carrier diffusion equation and try to solve some example. Okay. So here we have this long bar of silicon, and we know this delta P sub n is fixed at x equal to 0. So at x equal to 0, it's fixed to a certain value. And try to find this delta P sub n as function of x, right? How does this change inside the silicon? Okay. So to solve these questions, right? Solve these examples. The first step is always try to decide which case is appropriate. Okay. So go back to here. Which one we should use? Right. So we have silicon and the certain value fixed at x equals 0. Okay. So which one? Which solution? we should use? Yes.
Before,
The fourth one? Why?
because we have delta P.
Yes.
So is the origin concentration.
Yeah. So we have this delta P, right? It's fixed, right? It's fixed at origin. So what does this mean? It basically means this value does not change with time, right? It's fixed. It does not change with time. So this basically time derivative is 0. So what does this mean? It will be the steady state, right? Steady state means time derivative is 0. Okay? And we have these threes, right? So the fourth one is the right, so we choose these one of them, right? So which one we should choose? The third one? First one? Why?
Because the problem is saying about a concentration gradient.
Yeah. And also, yeah, let me show you. So this one, the first term is independent of time, it's steady state, right? And unless state otherwise, by default, there's no light. Okay, by default, there's no light. And also, by default, there is a recombination. Okay? By default, there's no light. By default, there is recombination. So then, basically, this first one. Okay, so this is the first case. And for the first case, this is the general solution. Right, so we'll use this general solution here and try to find the exact value for A and B. So we want to solve for A and B. And to solve for A and B, we need to use the boundary conditions. What are the boundary conditions we can use?
X equals 0.
Yeah, exactly. So x equal to 0, we know the value, right? When x equal to 0, we have delta p sub n equal to this delta p sub n. Okay, so this is one boundary condition. Because we have two unknowns, right? We need another boundary condition. What are the other boundary conditions? Here we only have one, right? We only know this. So now, think about x at infinity, right? When x equals to infinity, what's the value for delta p sub n?
Is it 0?
0. Why?
There's no more holes
Why there's no more holes?
because it's really far away, like the length of it.
Yeah, why it's far away than due to what? Think about we have recombination, right? So the holes cannot travel to a long distance, right? Eventually it will recombine, right? Recombine with electrons. But if we give it the hole enough distance, it will always recombine with a hole with electron. Okay, so due to recombination, these holes cannot reach infinity length. Right? So these holes will always go to 0 at infinity due to the recombination. Okay, So now we have these two boundary conditions, and we can get this, solve this easily, right? So let's try to do it together. So when this, okay, let's use this one first, right? So this delta p sub n, and we have a exponential minus infinity over L sub p plus b exponential infinity over L sub p is equal to 0, right? In order to satisfy this equation, because this exponential, negative infinity, so this is basically 0, right? So in order to satisfy this equation, this exponential infinity is like infinity, right? So then it indicates that this b must equal to 0, right? Otherwise, this equation cannot be satisfied, right? So b must equal to 0, and then we can this delta p sub n is a exponential minus x over Lp, right? And then with this one, we can use this first boundary equation. When x equal to 0, this exponential term will be equal to 1, right? Exponential term is 1. So then delta p sub n equal to a 1, right? So then a is delta p sub n. Okay, so now then basically the final solution will be delta p sub n equals delta p sub n exponential minus x over L sub p. Okay, so this is the final solution when we use this boundary condition. Okay, and this tells us this excess carriers at x decays away exponentially into the bar with decay length like L sub p. Okay, so it's exactly like this, this blue curve. Okay. All right, so this is this first example, and also since we know this, right? If we know this excess carriers, how does it change with position? Then we can also determine this minute carrier current. So what's the current? What's the expression for current? Anyone still remember? So for this minute carrier current, we are in the diffusion current or drift current. Diffusion, right?
It dominates.
Yeah, exactly. So remember, we made several assumptions, right? So the first assumption is the diffusion current is much larger than drift current, right? So if you forgot, then just go back to show you. When we derive this minute carrier diffusion equations, this is first assumption, right? So diffusion current is much larger than drift, and we can already get the expression for the diffusion current. Okay, and also based on these assumptions, also we can rewrite this like this. Okay, so based on these assumptions, this is a diffusion current, and you can see the current is basically determined by how does this delta p sub n change with x. Right? And since we already know this expression, right? So we already know this, then we can just use, right? The current is this, then we can calculate this value, right? So let me just also show you here. So it's J is related to the derivative, right? So it's minus Q d sub P, and it's d delta Pn over dx, right? And we know this delta Pn, the expression, right? So the derivative with respect to x will be delta Pn, and this derivative of this exponential term will be this exponential term minus x over Lp n times minus 1 over Lp, right? Right? So then it will be this 2 minus sign cancel out, so it will be Q d sub P over L sub P and of delta P sub n exponential minus x over L sub P. Okay, so this is current. Okay, so this will be current, right? And this will be here. Okay, so now what's the current when x equal to 0? So when x equal to 0, this exponent basically plug in x equal to 0 to here, right? So exponential 0 is 1, right? So this j x equal to 0 will be just q dp over lp delta p sub n. Okay, so this is a current when x equal to 0. Okay, so this is very useful because this tells us there's a way we can change the current, right? So because you can see this especially this Lp, right? This L sub P, there's a way we can change it. So this is a recombination lifetime, and we can either increase or decrease it. So this recombination of length, we can either increase or decrease by doping. And by doing this, we can modify this current easily. Okay. So here I just want to show you how does this Lp, this diffusion length or recombination length changes with doping. Okay. So here is you can see this is doping concentration, right? And this is I think y is so this is diffusion length, and this here the left axis, y-axis is lifetime, right? So you can see general trend, right? If you increase the density, the donor density, you decrease the lifetime, and also decrease the diffusion length, and this can be changed by several order of magnitude. Here you can see, for example, for this diffusion length, you can change from this, like here, it's like 0.1, like 0.1 centimeter, right, to 10 to the minus 5th centimeter. You can change it by 4 orders of magnitude. So this is very helpful. You can control this and adjust the current in PN junction. Right? Okay, so now let's move on to the second example. So for second example, we have a short bar of silicon extending from x equal to 0 to x equal to w. Okay, and we know the boundary conditions. So when x equals 0 and x equals w. So first, let's decide which one of these 4 solutions we should use. 1, 2, 3, 4. Which one? So first, let me ask you: is it a steady state case? Is it a steady state? Yes, right. So because these values are fixed, right? So the boundary values are fixed, and by default, there's a light or no light. No light. Right? By default, there's no light, and by default, there is recombination. Okay, so then which one we should choose? Yeah, one. Yeah. So we still use the first one. Okay. Right. So you still use the first one, steady state, no light, and this is a general solution. Okay. So just use the general solution, and in this example, we already know 2 boundary conditions, right? So we just solve, use these 2 boundary conditions. We can solve for A and B. Okay, so basically, it's when x equal to 0, then this delta Pn is this term, right? When x equal to W, then the delta P sub n is 0. Okay, so use this. So we can write out these 2 equations, and we have 2 unknowns. So we can solve for this A and B. Okay, so these are the solutions for A and B, right? And just plug in, right? So we can get this general solution. This is a general. Sorry, this is the solution, not general solution. This is the solution for delta P sub n. Okay, so actually here we can factor out this delta P sub n, and also exponential W over LP minus this negative W over LP. Okay, and by doing this, we can, this term, right? So this term here, or this term can be written as this sinc function. Okay, the sinc function is exponential x minus the exponential negative x over 2. Right, so these are 2 sinc functions we can rewrite. Okay, so we can get this expression here, and this show us how does this excess carriers change with position, and we can actually plot this plot this out. Right, so this will be the solid line here. Okay, this solid line here. So, and this is the how does this change? So basically, it's similar to what I will show here. So it kind of decays and goes to 0. And you may wonder what this dashed line, right? So this dashed line is kind of linear function, and it means that there's no recombination. So here, this dashed line represents no recombination. Solid line represents with recombination. So you can see if we have recombination here, which is by default we have recombination, the actual distribution snags below the linear graph. Okay, it drops much faster. Okay, so these are the example 2, and for this example 2, we can consider like a very extreme case. Right? So let's consider a very short bar. And for this short bar, this width here, the width is much larger than the diffusion length. Okay. And then you can see this W is much like W over LP or W minus X over LP are both smaller than 1. Because this LP, right, is very large. So for this case, then the sinh function, right? So this sinh x is approximately equal to x, right? For the small x. So now we can see for this solution, we can just replace this sinh, right? By this, here we can replace this by W minus X over LP, and here this can be replaced by W over LP. Okay, so you can see in this case, we will have a very simple solution. So we will have this, minority character concentration is kind of, a linear function, right? So it's because it only changes linearly with X. Okay. And this is identical to this this solution 2 of minority carrier diffusion equation. Right. For solution 2, this is a general solution. We have A plus bx, and we have here this is same form, right? So for this equation, this is valid when there's no recombination. Right? And this is actually true for this example because we have this width, right? So this width is much smaller than L sub P. This L sub P is a diffusion length or recombination length, right? So if the sample width is much smaller than the diffusion length, it means that this recombination can hardly happen. Right? So basically, it means there's no recombination in this case. Okay, right? So basically, this no recombination can happen because the bar is much shorter than the recombination length. Right? Okay. So now we can just compare these two cases, right? So we've got this, the solid line is due to, with recombination, and this dashed line is without recombination. Okay, and we know these are two, carrier concentration distribution for these two cases. So now my question will be, which minority carrier distribution results in a large current at x equal to 0? So which one? So the solid or the dashed line? Let's solid or dashed line. Yes, we have dashed one. Why?
Because I think that the NCDE1 is with sinus, like hyperbolic sinus, so it's not proportional, but for NCDE2 it's more proportional.
Okay. So think about what's the expression for current, right? So what's the expression for current? This is the expression for current, right? Right? So this is the expression for current. So it's related to this, the gradient, right? In this minority carrier concentration. Right? So the gradient, if you look at the figure, basically it means the slope. Right? So basically it means the slope. So look at these two lines or two curves at x equal to 0. Which one has the largest slope? The solid line, right? Solid line has the largest slope. Right? And this, if there's a large slope, it means the current will be larger. Okay, so basically the current is proportional to the slope. Right? Okay. Right, any questions for this? Basically, this carrier distribution with recombination can lead to a large current at x equal to 0. Okay? Right? Okay, so now let's compare these two two cases for this current when x equal to 0. So we have a very short bar or long bar. So for short bar, this length, this width or length is much smaller than the recombination length. So for long bar, this L is much smaller, right? Okay. So basically here, there's for short bar, there's no recombination, and for the long bar, there's a recombination. And we can, for the short bar, we already got this solution, right, for delta P, and this would be the current, right? Then take the derivative. If we take the derivative, this will be, this d delta p sub n over dx will be delta pn times negative 1 over w, right? And then we'll get this expression. And when this x equal to 0, then the current is given by this term. And for very long bar, we also showed you this solution here, right? So this is the solution for long bar here. And we use this carrier distribution. We can also calculate the current at x equal to 0. And you can see these two terms are very similar. The only difference is here we have W and here we have L sub P. Okay, so now we can just compare these two currents quantitatively. And so this is the current for long bar. Sorry, this is for short bar, and this is for long bar, right? And we can, calculate their ratios. So this JP for short over JP for long bar, and if we, take the ratio, you will see its proportion is equal to, LP over W. And this, because this W here, this W for the short bar, W is much smaller than LP. Right? So this ratio, the current ratio here is much larger than 1. Okay, so it means that for the short bar, the current is much larger. Okay, and again, here try to similar for this example here. Just remember that the current is proportional to the gradient of this excess carrier. Okay? Alright, so to summarize, we discussed the general continuity equations, and for the general continuity equations, we consider the minority carrier case. And this basically minority carrier diffusion equations. And we have introduced these notation, and we made these three assumptions. Okay, so make sure you understand the low-level injection. Okay, so we will definitely have a question in the midterm exam. Okay, so make sure you understand, whether the system is in low-level injection or not. Okay? And then we get this minor carrier diffusion equations here, and also we discussed the 4 cases. Okay, you know this. We have these 4 solutions, and for this, for we will also maybe have a question in the final exam relating to this. So make sure understand what's the step, right?
Wait,
For given example,
midterm or final?
midterm.
Okay.
Yeah. For given example, always try to find which solution you want to use, right? Based on the given conditions, choose this one of the solutions, and then based on boundary conditions, solve for A and B. Okay? Alright, I think that's all for today. Any questions? Yes.
How many questions did you
I haven't, pitched this next week, but I think you will have enough time to finish it during the plan and planning. I will provide more information during the in the next